Hey guys, so what we're going to be talking about today is an introduction to limits. I just want to do a really quick recap of what we did in class a couple of days ago. We talked about how in the world can I estimate slope when I only have 1 point. So we talked about a couple of methods. Somebody mentioned that you could come up with a equation that represents slope just by using what we know. We saw the slope was 0 at pi over 2. And we know that cosine of pi over 2 is also going to be 0. And so somebody did derive that the slope equation would be cosine. That's really advanced stuff. What I really just wanted to talk about was if you want to find a slope at just 1 point, the best way to find a slope at just 1 point is probably to use 2 points that are super close, called a secant line, and use those 2 points to approximate the slope. The closer that you pick your 2 points to be, the better the approximation. We also talked about how that's the same concept if you translate it to area under a curve. The more rectangles that you use, the better the area approximation is going to be. Now, what I want to talk about today is the limiting process. So what's the mathematics behind the limiting process? We talked about how with the area under the curve, the more rectangles that we have, as the number of rectangles approaches infinity, we can see that the area under the curve, the approximation is going to get closer and closer and closer. And in the same way, as the distance between these 2 points get closer and closer together, or in essence, as they approach 0, we get a better approximation. And that's called the limiting process. So we want to talk about the mathematics behind the limiting process. So the first thing that I want you guys to do is I want you to find the maximum area of a rectangle if I know the perimeter of the rectangle is 24 inches. I want to know what's the max area I can have if my perimeter is 24 inches. So go ahead and pause the video, talk with a friend, and see if you can come up with the dimensions of a rectangle that has perimeter 24, but has the most possible area. Okay, so hopefully you've had some time to think about this. So one way of approaching this is to think to yourself, what are the possibilities for me using 24 inches to create a rectangle? So the first thing that I'm going to do is I'm going to go ahead and draw a rectangle. We're going to talk about the possible dimensions. So the best way to do that is probably to think about it kind of like this. I have a rectangle. The perimeter is 24. So I need to have the same length, so 2 of those, and the same width, like this. So some possibilities that I might have, well, maybe width is equal to 10. Well, if width is equal to 10, then length has got to be equal to 2, like this. And so a possibility could be length is 2, width is 10, and so 2 times 10 is 20. So that's a possibility, but maybe it's not the best possibility. So I want you to try to think about what is the best way of finding the best possibility. Well, it might actually involve listing all of the possibilities. So go ahead and see if you can list all of them. Okay, so after listing all of these, we can determine that if length is 1, width would be 11. If length is 2, width is 10, etc., etc. So notice here how the biggest number that we get is 36, and we can disregard everything after 6 times 6, because after 6 times 6, we go back down to 35. And so this is not a totally conclusive proof here, but it's most likely that our maximum area is going to be something such that length is 6 and width is 6, giving us a total area of 36, which is going to be a maximum area. So we'll say 36 inches squared would be our maximum area. Okay, so you might think, what does this have to do with limits? Well, it actually has a lot to do with limits. So imagine that I didn't know what was right here. So imagine I have this exact same table, but this time I don't know what is here. A limiting process basically takes a look at what is going on from both sides. So as I'm coming down this way, what number am I approaching? And as I'm coming up this way, what number am I approaching? And so it seems like the number would be something around either 35 or 36. So if I'm going 11, 20, 27, 32, 35, I'm slowing down. The number that might be in here is probably a number bigger than or equal to 35. Same thing, if I extended the table, which I know I ran out of room here, if I'm coming from the top here, it's actually just a reflection. I would have gone 27, 32, 35. So I could conclude that the number in here is probably 35, or maybe it's 36. Who knows? It could be some combination, but using the limiting process here, if I didn't know that piece of information, I could probably guess very closely what the number actually would be. And that's basically what a limit is. So let's talk about it more concretely. I want to do limit notation. So I want to go ahead and give you guys a way to express this limiting process. So here's how we express a limit. We're going to write it as such. Limit, we're going to write as LIM. And then underneath the limit, we're going to write X with an arrow. So right now, this reads, so if we're going to write it as a statement, this reads right now, the limit as X approaches, and let's just come up with just a random letter. We'll say C. So the limit as X approaches C of, and so the of statement is going to be what I'm taking the limit of. We're going to call it f of x. So the limit as x approaches c of my function f of x is, and remember is, that's not new. Is always means equals. And maybe we'll say that the answer is L. So we can say the limit as x approaches c of f of x is L. And that is how we would actually, pronounce this mathematical equation here. So that is the notation we're going to be using from now on. So get yourself a little bit comfortable with that. All right, so let's keep moving. All right, so we want to talk about how can I estimate a limit numerically. This looks like a very scary mathematical equation, but it's actually an expression. But it's really not that bad. Really, what this is saying is we're saying the limit as x approaches 2 of the function 3x minus 2. So I'm actually going to sketch this for you guys so you can see it. So what this is saying is I have a graph, and the graph is 3x minus 2, which might look something, not steep enough. Let's do a little steeper. All right, so 3x minus 2 maybe is the graph that looks like this. What the limit as x approaches 2 is saying this. What number does the graph approach when x is 2? So imagine that I have x is 2 right here. What number am I approaching? And this is kind of a two-sided question. It's saying, what number am I approaching from the left side, but what number am I also approaching from the right side? Well, if I want to know what the height is here, to find the height here, this must be f of 2, which is going to be 3 times 2 minus 2, which is 6 minus 2, which is 4. And so we can see that there's no holes or jumps or gaps here. It's really just a matter of plugging in. We can see that the limit from the left is going to be a height of 4, and the limit from the right, as I come from the right, is also a height of 4. And so we can say that the limit, as x approaches 2 of 3x minus 2, it's just the same thing as me saying 3 times 2 minus 2, which equals 4. So really, baseline limits are very, very simple. They're just a matter of plugging in. So let's keep moving. Next one. All right, estimating a limit numerically. So what I want you guys to do is I want you to try plugging in 0 and plugging in 1 to a and b. See what happens. Okay, so after plugging these in, you should see something strange happening. And this is actually where limits get a little bit more interesting. So as I plug these numbers in, I plug 0 in for a, I'm going to get 0 over the square root of 0 plus 1 minus 1, which is 0 over 0. So this is what's concerning here, is I'm not really sure what 0 over 0 is. Actually, to be more specific, I'm not sure what a number over 0 is in general. We would say that that currently is undefined. And we talked about that earlier this year when we talked about dividing by 0 with tangent. So we have an issue here. We have 0 over 0, but I'm going to argue that the limit might still exist. We just need to do some extra steps to find it. Same with letter B. So letter B, we're in the same situation. I'm actually going to choose letter B because it's a little bit easier to start with. I want you guys to go ahead and graph x minus 1 over x squared plus 3x minus 4. So on your calculator, let's go ahead and graph that. Let's see if I can get my calculator up. Oh, need to sign in, so we'll pop. Okay, so after graphing this, we should get something that looks kind of like this. All right, so the question is, what is the limit as x approaches 1? Well, what this means graphically is what is the value of y as I approach x equals 1. So I'm going to go ahead and highlight where x equals 1 on my graph. So notice here how x equals 1 on the graph actually looks like it has a value, so maybe it does exist. So what I want to know is what's the height coming from the left and what's the height coming from the right. So one way of doing this is actually to take a look at your calculator. On your calculator, I want you guys to go into table. So take a look at your table, press second graph, and you should see table. I want to take a look at what happens as I approach, I think we said in this case, as I approach 1. So you can see at 1, we get an error, but we do have numbers before and after. So what I want you to do is I want you to change your step or your table step so that it's even smaller so we can see a better picture. So press second window and you're going to see table start. I want to start at 1 because that's what I'm looking at. And I want to change my delta table, or that's the change in each step. So I want to only step 0.1 this time instead of 0.5. And we're going to press second graph again. So we can see 1 has an error here, but notice here that coming from the right or the left, I am at about 0.2, and coming from the left, I'm at about 0.19. So looking at this table here, I want you guys to estimate, what do you think the error should be? What should the limit be? Okay, well, looking at this table here, as I'm coming from the top, and in this case, the top would represent the right, my numbers are getting smaller and smaller, but they're not getting smaller by the same amount each time. If anything, you can see that I'm slowly approaching what looks like 0.2 on the right. Coming from the left, though, we can see that the same thing is happening, but in a different way. I'm at 1.92, and now I'm at 1.96, and so we can see that that number in the middle, the error number, is probably close to 0.2. And so what we can conclude is that using this table here, we could actually say that the limit itself, as x approaches 1 of this whole thing, is equal to 0.2. And we did that by using our table. Now, there are algebraic means of doing this, and we'll talk about them later. But for now, we can use a table to figure out what a limit is, even if it initially does not exist. Okay, so what I want you guys to do next is I want you to use the same process to evaluate A and C using a table. So first thing you need to establish is that the limit didn't exist already, and you just do that by plugging in. If you get 0 over 0, we call that indeterminate form. So this is a little FYI I want to add in here. We call 0 over 0 indeterminate form. And the reason we call it that is it's basically undecided whether or not the limit does or does not exist. So if you end up getting 0 over 0, you should be pretty happy because there's a chance that the limit exists. You just need to prove it. And in this case, I want you guys to use your calculators to prove it. So go ahead and start that. Take a pause. Okay, so taking a look at letter A, if you graph this function, you're going to get the image that's listed right here. So if we're looking for the limit as x approaches 0, what we're looking for is basically what's the value that I approach from the left and from the right at 0. So what I did is I took a look at my table and I approached 0 using just 0.1 intervals. So you can see that as I'm coming from the bottom, I'm getting pretty darn close to 2, 1.94. And as I'm coming from the top, I'm getting close to 2 again, just from the other side, 2.04. And so according to this table, the limit as x approaches 0 of my function is going to be equal to what looks like 2. Okay? So let's move on to the next one. The next one is pretty interesting, actually. So if I use my calculator to graph this here, I'm going to get this image, which you can see actually, it looks pretty strange at 1. You can see that there's not really a set point at 1. If anything, it looks like there is an asymptote. which is probably not good news for our limit. And so using my table on my calculator, you can see that as I approach coming from what is the left, like this, you can see graphically and on the table that I'm getting lower and lower and lower and lower. And if anything, I'm probably going towards negative infinity. But as I come from the right, which is coming from the right here, you can notice that I'm getting bigger and bigger and bigger and bigger, and I'm probably going up to positive infinity here. Notice how 22 and negative 18 are not anywhere close to what's called convergence, or kind of lining up at the same number. And so what we can actually say here is actually one of my favorite phrases from Mean Girls, is that the limit does not exist. And the reason we can say that is that it's completely different from the left as it is from the right. So as I approach coming from the left, I'm going down, 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 down to negative infinity. But as I approach from the right, I'm going up, up, up to positive infinity. And so we can see that this limit is not possible. There is no point that it converges at. It actually hits at an asymptote, and therefore there is no limit. And so we can say it does not exist, and I like to write that as D and E. Okay, next one, I want to talk about how can I use a graph to find a limit. So this should remind us a little bit of what we did earlier this year. This is a piecewise function. So the first thing that I want you to do is I want you to graph the piecewise function A and see if you can graph the piecewise function B. Okay, so looking at these two piecewise functions, hopefully this was a little trip down memory lane. If not, this is a good review. We're basically saying that x is 2 for literally everything except 3. So I put a big old hole at x is equal to, oops, I actually messed that up. Let me fix this real quick. There's not a hole here, sorry. 3. So x equals 3 is where the hole is, my bad. Okay, let's fix that. Okay, so what this is saying is that the graph is literally y equals 2 for everything except x equals 3. At x equals 3, it says that there is a point at 0. And so my question is, what would the limit be? So what is the limit as x approaches 3? Well, here's what this means. As I come from the left, what is the y value my function is approaching? And as I come from the right, what is the y value that my function is approaching? Well, we can see that it's approaching the same y value. No matter what's in this hole here, as I get infinitely close to the hole, I am at the height y is equal to 2. This hole, or this missing point right here, actually plays no role. So this is actually meaningless. In fact, we'd say that this hole right here, meaningless, is meaningless. The limit as x approaches 3 of this function, f of x, is actually 2. And it's 2 because the height from the left and the right is unaffected by this hole. And the same thing happens in the next function. We have f of x, and the limit as x approaches 2 here, and I actually messed this one up too, so let me fix this. Let's fix this again. The limit as x approaches 2, which is this graph right here, my bad. Well, what I want to know is what happens from the left and the right. Well, an arrow coming from the left, notice how the hole doesn't really affect the arrow. The arrow is going to get infinitely close to the hole, I never touch it, and the arrow from the right is going to do the same. So we can see that both arrows are pointing to the same place. They're pointing to a height of -3. And so the limit as x approaches 2 of f of x in this case is -3. So I'd say the moral of the story in this one here is that holes don't matter for limits. So holes don't matter for limits. And that's kind of the big takeaway here. So holes don't matter for limits is our big takeaway. Okay, let's keep moving. All right, so next one. The limit fails to exist. So we've been talking about all these places where limits exist, which means that there must be some places where they don't. So here are some options for where the limit does not exist. Here's the first one. If I have a graph that looks like this, we call this graph a jump. We call it a jump discontinuity. So jump discontinuity. So what we're basically saying is it's not continuous there. So if I remember my roller coaster from previous lessons, to be continuous means I keep my pencil on the paper. So I would have lifted my pencil up here. That is a jump discontinuity. Okay, so let's talk about why the limit doesn't exist. Well, the limit as I'm coming from the left looks like the arrow is approaching whatever this number is. We'll say it's 3. But the limit as x approaches from the right, look how the arrows don't meet up. So basically your goal here for limits is you want these two arrows to be pointing to the same place. And clearly they're not pointing to the same place. And so we'd say the limit doesn't exist. Here's the next one, and this is one we've actually just seen. The next one looks like this. Imagine I have a graph that looks like this. So we can see that there is an asymptote going on here. We would say that this limit doesn't exist because it has what's called an asymptote. It doesn't exist because, well, let's take a look at our arrows. As I follow the graph from the left, my arrow goes up. But as I follow the graph from the right, the arrows go down. So the arrows are nowhere close to meeting, and so the limit doesn't exist here. So that's the second one. The last one is just a little fun fact one. You'll probably never see it. It's called oscillating, and it might look something like this. Okay. So basically what we're saying is that we're oscillating really, really close up and down here. And so the limit wouldn't be the same on both sides. You probably won't see that one, but it's a fun fact. So this one's called oscillating. See, guys? Okay. So what I want you guys to do next is I want to take a look at A and B. I want you to evaluate them initially, see if they exist, and be looking for 0 over 0 form. So if you can find 0 over 0 form, which is called, oh my goodness, I can't remember, which is called indeterminate form. Indeterminate form is your key to seeing if something might possibly exist. So indeterminate form, okay? So what I want you to do for A and B is evaluate them, see what you get initially. Okay, so you should have tried that already. Let's go ahead and evaluate. What we're gonna get here is 0 over 0, which is indeterminate form, so it's possible. Second one here, cancel out that 0 and plug in a 1. You're gonna get 2 times the absolute value of 1 minus 1, which is 0, over 1 minus 1. So we get 0 over 0 again, which means the limit might exist. We just need to show if it does or doesn't. And what we're going to do here is we're going to graph this to know for sure. So what I want you guys to do is take your calculators and I want you to graph both functions and see if they exist left to right. Okay, so taking a look at letter A, I graphed this function and notice here how as I approach from the left, my arrow goes here. But as I approach from the right, my arrow goes here, which we can see that the arrows are not the same, and so the limit doesn't exist. And so more formally, we're going to try to make a habit of this from now on. We're going to introduce some new notation here. We're going to say that the limit as x approaches from the left is going to be written as this. We're going to say limit as x approaches 0 and put a little negative above it. That's going to imply that I'm approaching the limit from the left. Well, the limit as x approaches 0 from the left of my function, we'll call it f of x. It looks like the arrow's pointing to maybe like -1, but the limit as x approaches 0 from the right, which we'll use a positive to denote, well, let's take a look at that. That looks like it's approaching +1. And so what we can see is that these two are not equal, and because they're not equal, we would say that the limit does not exist, or you could say DNE, okay? Go ahead and try the same process for the next one. See if you can more formally prove that the limit does not exist. Okay, so taking a look at this next one here, letter B, we can clearly see the limit doesn't exist, and it doesn't exist because there's what's called a jump discontinuity. But I want to be more specific about that. So I'm going to use limit notation, left and right limit notation to prove it. We can say the limit as x approaches what looks like 1 from the left. Well, let's see what that is. My arrow approaching from the left looks like it's approaching about -2. So the limit as x approaches f of x from the left has got to be -2. But the limit as x approaches 1 from the right using this notation, well, let's take a look and see what that is. Well, if I follow my arrow as far as I can go, it looks like it's approaching about +2. So once again, we can see that these are not equal, and so the limit does not exist. Okay, so that's the more formal notation. We're going to try to hopefully get used to using that. All right, next thing. Unbounded behavior. So we've talked about finding limits using a graph or using a table. We're going to talk about how could I find a limit that doesn't exist, and how could I be more specific about it, not using a graph or table from my calculator. So let's go ahead and take a look at this one. Well, this first one here actually does work. Change this 1 to a 0. So this is the limit x approaches 0, and this one is also the same thing. We're going to get 1 over 0. So notice here how that is not the same as 0 over 0, and I'm actually going to draw a little rule for you real quick. Basically, if you get 0 over 0, if you get 0 over 0, it's indeterminate form. It's indeterminate form. But if you get a number over 0, then for sure the limit does not exist, or it might do something a little bit different. It might approach what's called infinity, which I don't know why I said that. You know what that is. Or it might approach negative infinity. So we're going to talk about which one of them it could be. Infinity. All right, well, to figure out which one this could be, you could graph it, but imagine we don't have a graph and we want to know what does this limit do. We already plugged in 0. We didn't get much out of that. So what I want to do is I want to find some left and right-handed limits. To manually find a left or right-handed limit without using your calculator, you're going to pick a number that's really close from the right and a number that's really close from the left. So a number that's really close from the right that approaches 1 might be like 0.1, and a number that approaches from the left that's really close might be like negative 0.1, right? So those are both very close to 0 from the left and right. And then I'm going to plug them in. So if I plug something in from the right that's super duper close, let me give myself some more space here. I'm going to get 1 over 0.1 squared, which is going to be 1 over 0.001. I think, is that enough zeros there? Anyway, so we can see that I have 1 over a very small number. But 1 over a very small number, this is the same as 1 over 100, which it should be. I think I actually messed my zeros up there. 1 over 100. Well, 1 over 1/100th. Sorry, I gotta double this. Sorry. This is the same as 1 over 1/100th. If I keep it, switch it, flip it, it's 1 times 100 over 1, which is 100. So we can see this number is actually quite large. And in fact, if I got even closer, say I did 1 over 0.01 squared. I did that. Well, then I'm going to get 1 over 1, 2, 3, 1, 2, 4, maybe a 1 over 1/1000th, like this, which would multiply to be 1 times 1,000, which is 1,000. And so we can see here that as I get closer and closer to 0 from the right, I'm getting bigger and bigger. And so I must be approaching infinity on the right. Let's try the left. So if I try approaching on the left, we established that that was going to be negative 0.1. That would be really close from the left. Well, you're going to see here the property of squares is really going to make this the same problem. 1 over negative 0.1 squared, negative 0.1 squared, it's going to be 1 over basically 100th, which is still 100, right? Because a square is still going to be positive. So if I try that same process again, I'm also going to approach positive infinity. So what we can see is that the left side equals the right side, and so the limit kind of doesn't exist, but it does. And so by saying that, we're saying it doesn't approach an actual number, but it does approach something. It approaches infinity. And so we can say that the limit as x approaches 1 over x squared, so let's write that out a little bit better. We can say that the limit as x approaches 0 of 1 over x squared is equal to infinity. Or we could say it approaches infinity. So instead of it approaching a number, it still technically doesn't exist, but it does approach something more specific, which would be infinity. So what I want you to do next is I want you to find this exact same thing using the limit as x approaches negative 1 over x squared. So go ahead and try that one. Okay, so we can see that actually the same process is going to be applied here. All we're going to do is put a negative out front. So this time, instead of everything approaching positive infinity, we can see as we get closer and closer to 0, we're going to keep getting more and more negative first 100 and then 1,000 and then 10,000, et cetera, et cetera. And so we can say that the limit here as x approaches 0 of 1 over x squared, but negative, is the same thing except it's negative infinity. So what we can conclude here is that this negative sign that we have out front, notice how these limits are the same, can actually be brought out front and we can take the limit traditionally. So this is the same thing as the negative limit as x approaches 0 of 1 over x squared. So same thing. So basically if there's a constant out front, I can actually move it, take the limit, and then multiply later. Okay, so let's go ahead and try just a couple more, and these ones are just special cases that you're just going to have to memorize. So taking a look here, we have the limit as x approaches 0 of sine of 1 over x. So that's going to be sine of basically 1 over 0, which who knows what that could be. So what we want to do here is we want to figure out what this is. Best way to figure this out is probably by graphing. So let's go ahead and graph this. Make sure you're in radian mode. So we're going to get sine of 1 over x graph. And I'm going to kind of zoom in and see what happens. So let's zoom in. Okay, zoom in here, we get kind of a little jump that's going on within the graph. And so we want to use this graph to conclude what this must be. I'm going to zoom in one more time and see just to make sure. Wow, so there's actually a ton of oscillating going on here. So this is actually a little bit more complicated than we might have first seen if we didn't zoom in. So we see oscillating going on here. So we want to figure out what must this limit be. I want you guys to go ahead and decide yourselves. What must this limit be? And think to yourself, how am I going to justify this? Okay, hopefully you had a little bit of time to think. If we go back to the definition of when limits do and do not exist, notice here it says limits fail to exist when we have oscillation or oscillating. Imagine like fans oscillate back and forth. We can see the same thing is actually happening in our graph of sine of 1 over x. In fact, I'm going to go ahead and screen grab that and put that onto our notes. We can see a lot of oscillation happening here, and it's really inconsistent. So we actually can say that we don't know what this limit is. We don't know if it's negative infinity or positive infinity. It just straight up doesn't exist because of all that oscillating. So what I want to do next, I want you guys to try the same process. This time, let's find the limit as x approaches 0 of cosine. So go ahead and take a pause and see if you can find that one. Okay, so hopefully you had a little bit of time to figure this one out. Actually, this one is very straightforward, believe it or not, if you're careful about it. This is actually the limit as x approaches 0 is going to be the cosine of 1 over 0 minus 1, which is going to be the cosine of 1. Believe it or not, you can actually just evaluate that in your calculator. So let's see. Let's clear out of here and let's see what is the cosine of, I think actually negative 1. 0.54. And so this one right here, a little bit of a trick question. Just be careful. The reason I put that in there is I want you guys to be aware sometimes limits are extremely easy to take. Do not forget to initially plug in. So if you skip that step and you start doing all this work, you might actually miss a really easy problem that involves literally just plugging in. So just be careful about that. So that's the answer there. All right. All right, so I just want to talk about a couple of key takeaways for finding limits. And then that's pretty much it. You guys are going to be working on some practice. I know this is a long video, so we might work on practice next time too. All right, number one, key takeaway. I want you to plug it in first. We just talked about that. I gave you a little bit of a trick question here. Make sure you plug in first. Sometimes limits are really easy. All right, so there's two subpoints here. A, if you get 0 over 0, that means indeterminate form, which means there's a chance that the limit exists, but you need to do a little bit more work to find out exactly how it exists, if at all. B, if you get a number over 0, you basically have three options. You could have doesn't exist straight out. You could have infinity or negative infinity. And to prove that, you might need to plug in some points to the left and to the right to know for sure. Number 2, you need to prove limits exist on both sides. You can't just prove it on one side because every limit is going to basically exist almost on one side. You need to prove that it's going to the same direction on both sides, left and right. And number 3, if you do have access to a graphing calculator, I would definitely graph it and make a table. That's your best bet in finding an approximation. So those are the key takeaways for finding limits. I know this is a very long video, but this is a very actually brief introduction to limits, and we will talk more about them in deeper detail next time. So if you have any questions, feel free to send me an email or send me a remind.